So in this part, we're going to study how micro-machined inductors or RF MEMS inductors actually improve the performance. So I have given you in the next few slides a few different examples, and each one of those actually addresses a different part. So in this first slide, I'm actually giving you an inductor that essentially addresses the low frequency performance by making a very thick metal. So one of the techniques that was deployed early on in the literature was basically this idea of copper electroplating. And in this particular implementation, they were able to get a 10 micron thick copper in this quasi three-dimensional inductor. And that had a dramatic influence on the Q. If you actually check the quality factor of this device here, at about 4.5 gigahertz, it actually reaches a Q of almost 40. So which is roughly 4 to 5 times higher than the devices you've seen so far. And so you can see that not only it has a pretty high peak Q, but the Q is actually above 35 for an octave bandwidth, which is quite interesting. So this type of technique, once again, is the main path forward if you utilize a relatively low frequency where essentially everything is dominated by the thickness of the metal. Other techniques have actually focused on removing the substrate underneath the inductor in order to remove the parasitic capacitance. So a very common technique that is done is that you're using some type of a gas to etch the substrate. So here you can see a nice hole underneath. So that used to be a silicon substrate, but now through a reactive ion etching technique, which is essentially a dry etching technique, that substrate simply has been eaten away, which leads to a suspended inductor. Here you can see it schematically, and here you can see it in a 3D fashion, a suspended inductor on top of the substrate. Now, if you're asking yourself the question, how come this thing stays straight, right? This thing is a very thin metal inductor. It has practically no weight, and so the stresses of the metal are enough to basically keep it like that. In fact, if the stresses of the metal are even higher, you will see the inductor sometimes curling upwards or even downwards. But this is a pretty good technique if your main goal is to reduce the parasitic capacitance. And as you will see, the parasitic capacitance can actually be reduced quite a bit. So as an example, the Q increased from almost 4 that used to be at about 2 gigahertz to about 17, now at 8.6. And based on what we discussed before, now you can understand why both the Q as well as the frequency have actually increased. One of the techniques I particularly love is actually given in this graph. This is a technique that was actually developed in a couple of different places. One of the most successful implementations was actually right here at Purdue University. Professor Mohammadi's group actually came up with this interesting fabrication recipe where essentially it allows you to create a solenoid on a substrate. So if you look at this inductor right here, and here you can see a couple of the turns, or here you can see one of those turns, this is essentially a micro-machine technique where you print metal, and that metal starts by being perfectly flat. But at the minute you release that metal from the substrate by actually etching a sacrificial layer, there is so much stress in that metal that actually curls upwards. So the winding that you see here, it has actually been created by starting with a flat metal, highly stressed, and when you etch the substrate or a sacrificial layer, that metal naturally curls upwards, and the two sides actually come and meet right here. So you can see that this doesn't work just for 1 or 2 turns, but actually works for a lot of different turns, creating a very, very nice toroid. So what is interesting to see here is that you can control pretty much everything. So you can control the number of turns, you can control the diameter of this toroid, you can control the distance between the turns, but this technique has resulted into one of the best inductors out there. In fact, the team was able to measure a Q of over 100 for basically 1 turn inductor and a Q of over 70 for a 2-turn inductor at very high frequencies. The first one was about 15 gigahertz, the other one was about at 10 gigahertz. So it's one of the most successful inductors, and what you will see if you open these publications is that they have actually utilized this figure of merit, which is the inductance that I can get times the quality factor. And they got one of the best figures of merit out there, 150 and then 360.